Hello and welcome. You are looking at parallel and perpendicular lines. Okay, to begin, I've talked about a two-column proof before. In this, I'm going to be using a flowchart proof, which is a different way to organize your proof. And it's kind of listed or shown here below in a diagram. That's kind of how they're going to look. A flowchart proof is a web of items, like so, that lead to a conclusive math statement built on evidence. So just like a two-column proof, you're still making statements with reasons, and they build to other statements and reasons. The difference here is that in a flowchart proof, you want to connect bubbles when one statement is built upon a previous one. So let's say I make a statement here with the reason, and then I build upon that statement with another statement. This statement is irrelevant to these two statements. It has nothing to do with them. But then I can connect these two statements to make another statement and lead to a final statement here. So it's a little different two-column proofs in that it's not as cleanly organized, but it is very laid out in a way that shows how one thing leads to the next. Because in a two-column proof, you just have the numbers there, 1, 2, 3, 4, etc. And number 2 might connect to number 5 as much as number 4 connects to number 5. But you can't tell as you can here. In some flowchart proofs, I've seen them not give reasons and only give the statement, and I think that's kind of defeating the purpose of a proof. So you still write the reason underneath there and you connect. And like I said, it kind of gets a little cluttered, but flowchart proofs show how some statements are connected from others very fluidly. So in this particular set of notes, I'm going to be proving the theorems that are given in basically this video section. Like this one right here, and I'm going to be using flowchart proofs instead of two-column proofs for them. So here's a theorem that you'd want to know. If two lines are parallel to the same line, then they are parallel to each other. So if A is parallel to C and B is parallel to C, the statement is that A is parallel to B. And that can be proved using a flowchart proof. And it's not going to be a massive proof. All I'm going to do is give the given statement that A is parallel to C. I'm also going to make the statement here that B is parallel to C, also given. From there, I can actually make my final statement. So I made two statements that they were given. Now I can connect these two things and make the statement that A is parallel to B. So it's kind of weird that there's not much that I wrote in between, but the fact is that this is true. Why? You can either say that it's the transitivity property. I'd say it's a little more of substitution. B is taking place of C here, so I'm just going to say substitution. Transitivity would also work. But transitivity works from one to the next, etc. I didn't spell substitution right. You know how it's spelled. And that's your proof. That's it. That's your final statement. Here's another theorem. In a plane, if two lines are perpendicular to the same line, then they are parallel to each other. So if M and N are both perpendicular to T, the statement that we want to make is that M is parallel to N. This one's a little more than just making these statements, but I will go ahead and make them. Let's make the first two statements that M is parallel to T, or perpendicular to T, given. And N is perpendicular to T, also given. Next thing I can do is I can draw something based on that. Two angles that are perpendicular to the same thing are also congruent to each other. So I'm actually going to give two angle numbers here. I think I was supposed to do that and I never did. Angle 1 is congruent to angle 2. That is a theorem about right angles. All right angles are congruent. And that's a theorem we've already spoken of before. So that's the reason that angle 1 and angle 2 are congruent. Now, angle 1 and angle 2 also are corresponding angles. And when corresponding angles are congruent, that means that their respective lines that they're on are parallel. So you have a transversal, line T. You have lines M and N. You have two congruent corresponding angles. Doesn't even matter that they're right angles now. It just matters that they're corresponding and they're congruent. Line M is parallel to line N, because when corresponding angles are congruent, then lines are parallel. That's also not transitive, a biconditional statement, meaning if you had parallel lines, you could also say that the angles are congruent. But we found the angles are congruent first, therefore these two must be parallel. That's your final reason. And there's that flowchart proof. Once again, this statement doesn't connect down to your final conclusion. It connects to there. These two together help you make this statement here. I needed those angles 1 and 2, though. Sorry, I forgot them. Okay, one more theorem. In a plane, so here's your plane, the computer screen. If a line is perpendicular to one of two parallel lines, then it is also perpendicular to the other. So we know that T is perpendicular to M. We know that M is parallel to N. Let's go ahead and write those givens out. We have it there, right there, but I want to write it in flowchart proof so we can use it. M is parallel to N, and M is perpendicular to T. Okay. Now what I want to do is state something about corresponding angles. Last time I stated that this is biconditional, meaning before I said if corresponding angles are congruent, then lines are parallel. You could also say if lines are parallel, then corresponding angles are congruent. Well, this, as I didn't write, this angle 1 and 2 are corresponding angles. They would only be congruent if I have parallel lines, and we do. If I have parallel lines here, then I could say that angle 1 is congruent to angle 2 because parallel lines leads to corresponding angles congruent. So you see it's the exact opposite of the other way that it's stated. So angle 1 is congruent to angle 2. Now I did not need to know the fact that M is perpendicular to T to make that statement. However, now that I know that, I can now connect these two and say if M is perpendicular to T and if angle 1 is so if angle 1 is a right angle and if angle 1 is congruent to angle 2, then angle 2 is a right angle. So let me first start by saying angle 2 is a right angle. Reason, angle 1 is congruent to angle 2. And angle 1 is a right angle, as we know. I probably didn't have to say that. But anyway, so my final statement based on that, if that's true, then N is also perpendicular to T. Reason, because angle 2 is a right angle. So notice how I used a statement here with the reason. My reason became that previous statement. All right? That's how you can build on conclusions, by doing that. Say, make those connections. And that really works. I don't think I had to make this statement because otherwise somewhere I probably should have said angle 1 is a right angle as one of my statements. These could have just drawn to here. You would have been just fine. That's what makes it also perpendicular, because these congruent corresponding angles and this one being a right angle makes this a right angle, makes those perpendicular. Hopefully the flowchart proof thing's making sense. It's the same as a two-column proof, but you really get to make very visual connections with it. Okay, study what is given, what you need to prove, and the diagram, meaning study the diagram. Then write a flowchart proof. Okay, I have these three statements. They're all in the same plane. I'm going to write A is perpendicular to B, given. Also write B is perpendicular to C. I'll put the bubbles in a second, given. And then C is perpendicular to D, given. All right, let's add a little bubbles here, and then let's flowchart this. Okay, if A is perpendicular to B and B is perpendicular to C, then based on the previous theorem that we spoke about, if there are two perpendicular lines, if they're both perpendicular to the same line, then those two lines are parallel. This is like A perpendicular to B and C perpendicular to B. Therefore, we can state that A is parallel to C based on that theorem we just talked about. I'll call it perpendicular. Well, you know what? I'm not going to give it a theorem name, but it was that theorem, so I'll just put A is perpendicular to B and B is perpendicular to C. If that's the case, that makes that true based on that theorem. So if you make that kind of statement, that's fine. That helps work out and get that, because we proved this earlier when that happens. And if A is parallel to C, and if C is perpendicular to D, then A is perpendicular to D. Because, was it this one? Because of this one right here. If you have a line perpendicular, if you have C perpendicular, if you have D perpendicular to two parallel lines A and C, then A has to be perpendicular to D just as C is perpendicular to D, because A is parallel to C and C is perpendicular to D. I can state that because that was a part of this theorem. You could write out this theorem. There might even be a name for the theorem. I actually don't have it off the top of my head or know what it is, but I use these two to connect and bridge that. So what's really the issue here? A isn't really drawn all the way down. You could draw it all the way down and make more sense of it, but a diagram is exactly what it is, and you can't know for sure that's perpendicular unless you do a proof with it. So notice how things connected and how things were flown through. It was fluid. Good flow. All right, I just want to give some more examples here, some things that you might have questions about or have problems on. Each of the following statements describes a ladder, this one right here. What can you conclude about the rungs? The rungs are these guys right here, the things you step on and climb on. One side or both sides of each ladder, explain. So in this one, if the rungs are parallel, if these rungs are parallel here, and the top rung is perpendicular to one side, so the top rung is perpendicular to one side right there, what can you conclude? What I conclude about the rungs in one side is that all rungs are perpendicular to one side. How come you can say such a thing? Well, if you look at, I have to look back at which theorem it was. If you look, I think it's this theorem right here. If I have a bunch of parallel lines and I know that one of those lines is parallel to this transversal, then all of those lines have to be parallel to the transversal. So if these are parallel and this rung is perpendicular to here, then all of these are perpendicular to it. They have to be because they're all parallel to each other. So that's something I can state. I know nothing about the other side though and those rungs. For all I know, that might not be parallel or parallel to this side or perpendicular to the rungs. Okay, the rungs are perpendicular to one side. The other side is perpendicular to the top rung. So those rungs are all perpendicular to there. This side's perpendicular to here. First statement I can make is if this rung is perpendicular to both these sides, then both sides are parallel. And now that I know that both sides are parallel, this one here and this one here, if this side is parallel to a side that has all of these things perpendicular to it, then all of those must be perpendicular to this side as well. Once again, using those theorems. So drawing conclusions based on that. And all rungs are perpendicular, I'll just do the sign, to both sides. My handwriting here is not that good. So again, you draw conclusions based on the theorems we had. You can make statements based on that. That's 2. 3, each rung is parallel to the top rung. So all of these are parallel to the top rung. That means all rungs are parallel to each other. Now the question is there anything I can say about the sides? Can I say that I know the sides are perpendicular to the rungs or the sides are parallel to each other? No. In fact, let me change the sides and skew them. When I take this and rotate it a little bit, and this one and rotate it a little bit, does that change the fact that the rungs are parallel to each other? Not at all. So there's nothing that I can state about perpendicular to the sides or the sides parallel to each other. There's no such statement that makes that true for sure. This is the only information that's given. So going back, bringing it all back. Finally, number 4, the rungs are perpendicular to one side and the sides are not parallel. So the rungs are perpendicular to one side. So we already know that statement. We don't have to say that again. If they're perpendicular to one side and that side is the same side that they're all perpendicular to, then all the rungs are parallel to each other. And that's really the only statement you can make. All rungs are parallel to each other, just like the last one. We already know they're all perpendicular to that. But the other one states that the sides are not parallel. So we also know, I don't have to say anything more, but we also know that the rungs are not perpendicular. They're for sure not perpendicular to this side, because these sides are not parallel. They're perpendicular to one, so they cannot be perpendicular to the other. So it kind of looks like that. And that's kind of just the final statement there. So you've made all your conclusions that you could, and that's really it. Those are the things you know for sure, based on these three theorems, and we made connections with them. So you saw a few things about flowchart proofs, how they connect. You still need the reasons below. The reasons don't always need to say theorems per se. You can make previous statements based on the theorems that you know, and that'll be good enough. For instance, I made this statement, and that statement's based on this theorem proving that these should be perpendicular if these statements are true. So that's just kind of all this is, and then you got some example problems using these things. I hope those made sense as well. Fiend.